Imagine an object with a gravitational grip so intense that absolutely nothing can slip away. Not matter, not radiation, and not even light itself. This is a black hole. Despite being completely invisible against the dark backdrop of space, it exerts one of the most powerful forces in the entire universe. While a black hole begins as the collapsed remnant of a dead star, it becomes a region in space where the familiar rules of reality are entirely rewritten, placing it at the absolute boundary of modern science. To understand how these objects form, we have to rewind to the end of a massive star's life cycle. For millions of years, the star sustains itself through nuclear fusion, but eventually it burns through all of its available fuel. Without that outward pressure from fusion to keep the star stable, gravity takes over. It rapidly crushes the star's core under its own enormous weight, packing an incredible amount of mass into an impossibly microscopic space. This extreme concentration of matter is the exact trigger that births a black hole. The violent collapse leaves behind an inescapable gravitational pull, setting the stage for what happens if something or someone gets too close. If you are to travel toward a black hole, the first thing you'd encounter wouldn't be the darkness itself. You would be met by a chaotic, violently rotating ring of gas and dust. This is the accretion disk. As matter becomes trapped in orbit, intense friction and extreme gravitational forces whip the debris around, heating it to enormous temperatures. While the black hole itself emits absolutely no light, the surrounding material crashing into itself shines blindingly bright. This brilliantly glowing plasma serves as the final visible outpost of the normal universe, right before you hit an unseeable threshold. That threshold is the event horizon. It isn't a solid physical wall you would crash into, but an invisible mathematical boundary marking the exact point where the velocity required to escape exceeds the speed of light. According to Einstein's theory of general relativity, a gravitational pull this severe actually distorts the passage of time itself. This creates a bizarre split in reality. To an observer watching you from a safe distance, your descent would appear to slow down, eventually freezing entirely at the edge. But from your perspective, time would flow normally as you drift past the boundary and into the dark. Once you cross the event horizon, your connection to the outside universe is permanently severed. You are trapped in an isolated reality where the only possible direction to move is inward. So, what actually happens to your physical body once you are inside? If you fall into a smaller black hole, the gravity is highly localized. The downward pull on your feet is vastly stronger than the pull on your head. This creates a severe vertical stretching and horizontal crushing effect. Scientists call this spaghettification. A supermassive black hole acts differently. Because its scale is so immense, the gravity gradient is much smoother at the event horizon. You could float right across the boundary completely intact without noticing an immediate physical difference. Eventually, the result is the same. The inexorable pull guarantees a violent end, as all physical matter is dragged relentlessly deeper into the extreme core. At the very end of this descent lies the absolute center of the black hole, where gravitational forces are overwhelmingly infinite. Here we find the singularity. Our current equations predict this is where matter is crushed into an infinitesimally tiny region, causing the curvature of space-time to become infinitely large. But here is the truth. Scientists do not actually know what a singularity is. Under these extreme conditions, our known laws of physics break down entirely. A singularity may not even be a physical object. Instead, it functions as a mathematical red flag, signaling the exact limits of human knowledge. The core conflict is that the rules of quantum mechanics clash directly with Einstein's rules of extreme gravity. In this specific environment, neither framework works. This creates the black hole information paradox. It is the greatest unresolved debate in modern physics. If nothing can ever escape, what ultimately happens to the fundamental information of the matter that fell in? Researchers are actively searching for a unified theory of quantum gravity to explain what is really happening inside these extreme, crushed environments. Black holes are deep cosmic mysteries.
But they also serve as hard proof from nature that our understanding of the universe remains incomplete, waiting for the next generation of physicists to rewrite the rules.